Everybody caffeinated? I'm not enough. We're going to roll with it. All right, so we're going to talk about test flake, and I know this is something that triggers a little bit of PTSD in some people, but I feel like it's something as a community that we need to rally around and figure out what we're going to do about it. So what are we going to learn today? We'll talk a little bit about what test flake is, the various forms it takes, what problems it causes, why is it so hard to prevent, and what can we do as a community to stop it. So first of all, who am I and why should you listen to me? My name is Dave Cadwallader. I work at Walmart Labs in the automation infrastructure team. So we don't actually write tests ourselves, but we empower teams to run the tests that they want to write for themselves. We empower them to run those tests at scale in a way that's reliable, in a way that fits into a continuous delivery pipeline that can run all throughout the day. We serve more than just Walmart.com. We serve Sam's Club and Walmart Grocery, to name a few. Walmart has a lot of different pillars, as we call them, all over the place. You may have heard of this little company called Jet.com that Walmart recently acquired for a cool $3 billion. Jet is another e-commerce retailer, and we're now starting to work with them on their test automation strategy. So we've got a lot of people to support. And as of right now, last time I checked, we're clocking in at around 60,000 minutes of testing per day. That's about 41 days of testing compressed into a single calendar day. And so we accomplish that with massive scale parallelization and a suite of tools to make all this work reliably. So I wear two hats. The other one, in addition to working at Walmart, is I'm a co-creator of an open source project. It's called Test Armada. I've got some stickers up here. Feel free to grab some afterwards. And we don't make Test Armada is not a test library, so we don't care the language that you write your test in or the way that you express your tests. We want to take your existing test library and help to orchestrate it and make it work better at scale, make it work reliably, and leverage a common reporting infrastructure so that people who are writing tests in Ruby or Node or whatever can all sort of rally around the same add-on reporters and tools and orchestrators that can plug into this ecosystem so that we can all kind of share common strategies instead of being fragmented. So we'll talk a little bit more about that a little bit later. So the takeaways I'm hoping everybody will get today, understanding the various types of test flake, how we can use statistics and data visualization to help measure this test flake, how to squash test flake once you've found it, and how to get involved in a community-driven effort to end test flake. So I'm going to be recruiting everybody here to get involved. So let's talk a little bit about what does automation mean at Walmart and how does Flake get in the way for us. So I'm a developer. I'm making a front-end change. I push my change as a pull request to our internal GitHub Enterprise instance. A webhook triggers a build to run on Jenkins, and that triggers a whole bunch of parallel Jenkins jobs here. So we're doing linting, some static analysis, running unit tests. Accessibility tests is a big one that we've started doing recently. And then, of course, our functional UI tests based on Selenium. So each one of these tests, of course, is going to involve different things. They're going to take different amount of times. Some of them finish quickly, 30 seconds. Some of them take a few minutes. Functional tests, obviously, depending on the size of the test and how many browsers we're testing it on, these are going to take longer. But the important thing, which is something that was pretty ambitious that we decided to do, is that we wanted to actually run a full cross-browser functional test suite on every single pull request. And this is a big deal because at the end of the day, you've got a developer, and all they see really is that they've issued a pull request, and they're waiting, and they're waiting, and they're waiting, and they're waiting. And they don't really necessarily care about what's going on behind the curtain. They're just saying, I want to wait for my build to finish so I can check in my darn pull request, right? And so every single minute that we add onto that test suite is going to be time that they're waiting. It's going to be time that they're possibly grumbling and saying, we're holding back, development, right? And this is doubly true when things actually fail in CI. So when tests fail in CI, does anybody say, oh, wow, thanks. My app has a bug. What do we hear a lot, right? CI is flaky, right? It can't be that I have a real problem. It must be that something's flaky. So we've developed kind of this emotional, stressful reaction to this word flake because it gets in the way and it erodes confidence, right? So what are some of the problems caused by Flake? One of them, the biggest ones, for us is exactly that, confidence erosion. It's a growing mistrust of the systems that are designed to keep us safe in the first place. And as soon as somebody's infected by this mind virus that, oh, CI is flaky, this is what allows real application bugs to slip through, because as soon as people start ignoring test flake because the system is always flaky, they're less likely to actually go and investigate something. But why is Flake such a pain to deal with, right? So by its very nature, Flake is non-deterministic, something that, given the same input, exhibits different behaviors on different runs. This is really maddening. It's frustrating. There's different kinds of test flake. We have pass flake, fail flake, where sometimes it passes, sometimes it fails, who knows why. And then we have something that's a little bit more subtle sometimes called performance flake, where maybe the same test passes, but sometimes it takes a really long time to finish, and sometimes it finishes quickly. So what I'm going to ask us to do today, I know this is going to be kind of a little bit of group therapy here, but we're going to take Flake back. So we're going to turn Flake into a positive thing. And I want us to start saying this: hooray for Flake. Can you say this with me? 1, 2, 3. Hooray for Flake. So why the heck are we going to celebrate test flake, right? So anybody who's familiar with Google's notion of site reliability engineering, there's got a really great book on it. The thing they have on the first page is hope is not a strategy. So we can't keep hiding from flake. We can't expect it to go away. We can't be the ostrich with our heads in the sand. We have to acknowledge that flake exists, and we have to go hunting for it. And when we find it, we can measure it, and when we measure it, we can control it. And that's how we're going to solve this together. So let's go on a little journey to talk about how we first really stumbled with test flake at Walmart. So going back to this pull request thing, right? So we had, we're compressing a very high amount of testing into a small period of time, and we're trying to strive to keep compressing that so that we can run more tests without making developers wait a long time. So initially, we had some usage graphs that looked like this. So we use Sauce Labs for our browser as a service provider. And we can look at our concurrency graphs, and we can see something like this. Oh, somebody kicks off a build at 1 o'clock. We're running 30 tests at a time, and so we kind of get this plateau of usage. And if it's a really large test suite, it might even take a few hours to run, and then it dies off at the end, right? And then maybe a couple of developers at a time are all running separate builds. These are running on separate Jenkins boxes, and they all kind of stack up, right? And as soon as we got to 100, like at this time last year, I believe we were using about 100 concurrent VMs with Sauce Labs, we would start to max out our capacity, and this is where we called up Sauce Labs and said, hey, we need more capacity. So we went up to almost 1,000 concurrent VMs. And our graphs looked like this, right? So we were still seeing things stacking up. But just because we had 1,000 concurrent VMs that we could use doesn't mean that things were performing faster, right? We actually were still only orchestrating a relatively small number of tests on each individual Jenkins VM. So what we did here is we started thinking metaphorically, like imagining that this concurrency graph was like a bunch of sand, and we wanted to smush the sand castle, right? So we want to go from something that looks like this, a really short, wide sand castle of concurrency, to something that looks more like this, right? Like really tall, narrow. Basically, we wanted to have test suites that would burn a massive amount of concurrency really fast, really hot, and then finish all the tests, and then just exit and return the results. So basically getting as close to running every single test browser combination in our test suite all at the same time so that we can just get that result back really fast. That's the promise of high concurrency. So there's what we wanted. Anybody seen this on Pinterest? You use a blow dryer and melt some crayons, and it makes this beautiful, beautiful piece of art. So there's what we wanted and what we got. So here's what we wanted, right? We did all these design docs. We were like, this is going to be great. We're going to have these tall towers of concurrency, and we're going to run 1,000 tests in 5 minutes. It's going to be great. And and we'll be able to even fit more of these in a day because the chance of these colliding is going to be so small because they're going to be such thin slices of time. So there's what we wanted and what we got. And this, funny enough, looks like that melted crayons thing. But this is what our concurrency graphs looked like where we would have the expected really tall sandcastle, but then we'd have this like blob of concurrency at the end. And this is actually what it looked like on our graphs. And we were like, what the heck is going on here? So after a little bit of investigation, it didn't take too long to realize this is something that we started to call the retry tail. So we have a smoothing over strategy, like I'm sure many of you do, where when a test fails, you're like, well, there's flakiness, so we don't want false positives, so we're going to retry tests when they fail. So we do that. We're not proud of it, but it's something that is something that you have to do sometimes. But what that means here is that when we have extra rounds of testing that are tacked onto the end of a test suite, when one or more tests retries, that creates this tail, and it becomes more pronounced when you have higher concurrency. So this dream of high concurrency, test flake wasn't killing it, but it was kind of weakening the notion. And to understand why this is amplified at higher concurrency, I'm going to briefly introduce Magellan, which is a portion of Test Armada. This is our test orchestrator. This is how we orchestrate a massive amount of concurrency. Magellan has two main features. One is that it spawns out a massive number of child processes in your test library of choice to give you that massive parallelism. The second thing is that it adds fault tolerance, which is a fancy word for smoothing over test flake by retrying them. But the way that it works is basically this. You imagine that if we have a concurrency factor of 10, we have 10 Magellan workers, as we call them. Each one of these is a child process. And each one of them is picking off a test off of our queue of test browser combinations. Let's say that we have 80 tests that we need to run, and we're going to run them with 10 workers. So as the workers start to chew through them, we're getting some results. They're turning green. When a worker is done with a test, it moves on to the next one. What we wanted was something like this, where we'd have our 80 tests. They'd run across 10 workers, and so it would take 8 rounds of testing. And if we average about 5 minutes a test, we can predict that this is going to take about 40 minutes to run these 80 tests. So that's what we wanted. And what we got was something like this, where chances are the larger your test suite is, the more likely there's going to be a retry somewhere that's going to tack on another round of testing. So in this case, you can see we have a 9th round. So we've gone from 40 to 45 minutes. Not a huge deal, 12% increase in our total test time. But what happens when we're increasing our concurrency to something like 80 workers per Magellan run? So in this case, we're optimistically hoping to get everything done in one single round of 5 minutes. Now, as soon as we have one single retry, that's tacking on another round of testing. Now, comparatively, when we're going from 5 minutes to 10 minutes here, that's a 100% increase. We're doubling our test time, so that's more noticeable. We're not getting the same effect as we want. If we're so unlucky to have 2 rounds of retries, we could even be looking at tripling our test time here. So we really had to think about how do we cut this retry tail so that we can get the performance numbers that we want. And really, whether we're talking about 5% flake or 2% or 0.3%, all of these things have a retry tail. The only way that we can get to no tail is to get to 0% flake. So we've got a lot of work to do. Because at the end of the day, 1% flake might not cause failures if we can smooth it over, but it does cause perceived slowness. And that perception for our developers is what's really important when we're running these cross-browser test suites all throughout the day, every day, and developers are waiting for them. So every blip counts. And to combat these blips, we came up with something called BLOOP. Now, BLOOP is a reporter that hooks into Test Armada, so you can get this for free. It's not open source yet, but if you follow Test Armada on Twitter, we'll let you know really soon when it's open sourced. But what BLOOP is named after this phenomenon that was discovered by some underwater low-frequency sound detection in 1997, and some people initially thought that this weird bloop sound that they were hearing, like from thousands of miles away, was actually some like weird animal that was like bigger than a whale, and people were inventing all things about like dinosaurs still being alive under the ocean. Turned out to be ice quakes. Has anybody heard of ice quakes? It's really cool. It's like rapid freezing of glaciers, and it causes these like massive sound waves. Anyway. BLOOP is kind of interesting because it was this really mysterious thing. People were measuring it. They were trying to figure out what it was. Sort of like Flake, right? It's like, it's mysterious. We have all these theories about why it happens. But until we get really good at measuring it, it's hard to really wrap our heads around it. So at the end of the day, here's what BLOOP does. It takes all of our test orchestration that happens with Magellan. It takes each of these child processes, each of these Magellan workers that's running. It arms each of them with a reporter that sends UDP packets to a backing database. We use InfluxDB, basically with just things like, hey, I just ran a test, it failed, it took 30 seconds. Hey, I just ran a test, it passed, but after 2 retries, and it took 45 seconds. So it's sending these to a time series database so we can track these results over time, and we're using an open source data visualization tool called Grafana to visualize. Now, why do we use UDP? Just really briefly, network lesson here. TCP is a handshake method, so sending data requires that the remote server acknowledges it, and these kind of things can actually slow down the very thing that's doing the monitoring, right? So we didn't want the monitoring of our tests to actually slow down the tests themselves. UDP is also called fire and forget sometimes because it's not acknowledged. It's just blindly sending off packets. If some of them get dropped, no big deal. We're relying on a massive amount of these being sent. I could tell you a UDP joke, but you might not get it. Not as many groans as I thought I'd hear on that one. So let's actually measure some stuff, right? So what do we care about measuring the most? Flake rate. So flake rate we define as tests that eventually passed after requiring 1 or more retries. So here's a couple of flake rates that we've started capturing. So this is for our product page. We've got about a 3% flake rate. You can see the green on this graph here is tests that passed on the first try, yay. The kind of yellowish is tests that required 1 retry. There's kind of a slim little bit of orange here you can see. It's pretty rare that tests require 2 retries. Statistically, we see that doesn't happen too much. And then if a test retries 3 times in a row and fails all of them, then we consider that a true failure and we mark that as red. So we can see, across a few of our different product tracks here, the My Account team, they've got 2% flake. Homepage has 5% flake. This is the Walmart grocery. They've got about 4% flake. We're not counting the failures here towards that flake percentage. The flake percentage is only for tests that eventually passed after having to retry. So what we kind of have noticed anecdotally is anywhere between kind of 2 and 5%. It's just kind of normal baseline noise floor level of how flaky the system is, right? Another thing that we started capturing is the total suite runtime, because this is something, again, developers are very time sensitive to this. So this is the total duration of all tests in a suite. And we measure 2 different things here. We measure passing suite time. If the whole test suite was completely green, this includes retries and smoothing things over. If there's 1 or more true failures, so retrying 3 times and having 1 failure, we record that separately as a failing test suite. And we do this because there's some teams that are better than others about keeping their garden green, right? And we wanted to show that when you have failing test suites, that incurs more retries. That's a bigger tax on the system. It makes tests run more slowly. And so we wanted to show that it takes longer and makes your developers wait more to actually have test suites that are kind of untended. So we're applying some social pressure here to say, hey, if you don't want to wait so long, keep your stuff green. So you can see that for different tracks, we see different patterns. But something that we do see is kind of this really spiky result here, where even the passing test suite, it can fluctuate wildly between 8 minutes, 10 minutes, 12 minutes. And this was something that just kind of bothered us. Like, why is this happening? So we stitched all of this stuff together into these per-team operational health dashboards, as we showed them here. So the idea is to kind of let teams control their own destiny and observe their own statistics. But we gave this to teams, and they sort of like blinked, and they're like, okay, so things are flaky, things are spiky. Like, where do I even start? Right? This is just kind of overwhelming. And pretty much all of these pages were kind of similar, right? They were spiky. It wasn't really obvious what to do about this, right? So we drilled down another level. We started recording individual test timings. So this is not at the suite level. This is at the individual test level. This is kind of a crazy graph here, but what you're seeing, this kind of bright line in the middle is the mean of all tests running in the system. and then the blue kind of filled in areas are the upper and lower bounds. So we're kind of seeing a distribution of how long our tests are taking. But even this graph is still kind of doesn't really give us a lot to go on, because this is showing us system-wide all the tests that are running in the system. And when we're seeing this greater distribution here, we're not sure if that's because there's just different types of tests that are running at that particular time. Maybe there's some tests that are really simple that, by nature take less time, and there's some that are more complex that take more time. So we needed to go deeper and drill down and see individual test timings separated out per test. So what does that mean? So here's an example. This is for our grocery application. We've got 3 different graphs here, and these are actually 3 different tests. So the first one is resetting your password. The second one is logging in as a guest user. And the third one is amending your order and canceling it. And we can see that for these first 2 tests here, they're pretty consistent, right? You can just see on the graph, it's finishing in under a minute, sometimes spiking to about 2 minutes. Pretty much the same for the second one. But for this third one here, it's going kind of all over the place. Sometimes it's finishing in under a minute. Sometimes it's taking 5 minutes. And then we're spiking up into this red zone here. We color this red because we have a cutoff of 8 minutes per test. We say we're just generally based on how long tests are taking in our system. We say that if a test is taking longer than 8 minutes, you have to refactor that test to be smaller. And so if it's in the red zone, it's kind of in the danger of timing out for being a long-running test. So now we're starting to crack this open a little bit more and see that there's variation that exists, in specific tests that doesn't exist elsewhere. So this third test here, amend, order, cancel. Remember this one, because this is our friend that we're going to come back to and crack it open a little bit further. So we're going to keep on slicing this data more. And the reason why this is important is because, if you imagine that test flake is like a bruised apple, and we don't know which parts are sort of safe to eat, we can slice the apple to separate out the good parts from the bad parts, and we can use our statistics and data visualization to slice our data in the same way, looking to separate out what's flaky from what's not. Because if it's, instead of being this big overwhelming thing of like, oh, everything's flaky, if we can say, this stuff over here is good, this one test over here is flaky, that gives developers a much greater idea of where they can start looking for a problem. But when we're just looking at these lines visually, it's tough to do. So we really need some statistics to help us out. And I don't know about you, but I didn't really pay much attention in stats class in school. So I consulted this really awesome academic website to kind of remind myself about what I was doing. So standard deviation. Anybody remember this? It's a measure of how spread out the numbers are. So hey, this is perfect. This is a great thing for measuring flake. They even have this great example where they show you dogs, and you can like measure the standard deviation of different breeds of dogs. Basically, all you need to know is that standard deviation is a way of giving you a numerical value that tells you how spread out a sample size is, right? And InfluxDB, which is our backing database that we're using to store all of this data, just happens to have a great function called standard deviation that we can apply to a graph. We can even set some thresholds in Grafana. This is in milliseconds here, so we're setting a threshold of 10 seconds and 30 seconds so that we can take a graph like this and give it a nice little colored box next to it that tells us what the standard deviation is for that graph, and color-coded according to some relative notion of how severe that standard deviation is, how much variance there is. And so as expected, we're seeing that for these first 2 graphs, we've got a green and a yellow for like a low and a medium amount of deviation. And then for our friend amend, order, cancel, we've got a lot of variance here, and that's reflected in a larger standard deviation. So this is starting to give us better visual indicators of where we need to look. And when you zoom out and you're kind of looking at a whole test suite, this allows you to really quickly scan down the side and just see color-coded, where are my hot spots? Where do I need to look? It's a lot easier to do that than it is to kind of look at each of these lines and sort of say, well, I think that one's warbling a little bit more than this other one, right? So we want to help give people nice, clear visual indicators. So let's keep slicing some more. This was showing us variance in test time by individual test. Let's look at browser. So we can slice our data in a different dimension. The top graph here is showing us for that same grocery application across all tests, the difference between different browsers. So looking at IE10 on the top, IE11 on the bottom, we can start to see that this one actually surprised me. IE10 was performing better than IE11. We can look at all of our browsers in the suite, including Chrome and Firefox, and we can see that we've got some difference here, but really there's a lot of variation in all of these browsers, right? And when we have really, really spiky graphs, this doesn't necessarily help us, right? When everything is spiky, again, we need to kind of keep slicing to get to the point where we can see that there's clearly some outliers where some things are spiky and some things aren't. So let's try slicing in 2 dimensions here by individual test timings by test and browser. So here what we can do, we're looking at the same test on the top and the bottom here. This is one where we're checking for an invalid zip code, but we're comparing how that test performed on IE10 and IE11. So in this case, it's about the same. And we can see even across all 5 browsers in our suite, we don't really have a lot of difference here. Everything's roughly around 20-second standard deviations. So nothing really interesting to see in this test. But when we go back to our amend, order, cancel test here, and we're testing this one, slicing it by browser and by test, we can see that some of our browsers have a lot of variation, 1 to 2 minutes of standard deviation, while this other browser at the top, which I can't see which one this is now, but only 44 seconds of standard deviation. We can see on the right side too here, we're also capturing the minimum, median, and maximum test time. And so the variation is also reflected there. We can see in this browser on the top, it's only about a 60-second average runtime, but for these other ones, it's 2 minutes. So this is giving us some indicators of where we need to focus our time for looking at performance flake and where we don't need to look. So in addition to performance flake, right, we also talked about pass-fail flake. So this is another interesting one. So if we look at this invalid zip code test here, run across a sample of about 1,000 test runs, we can see that the number of flakes was pretty low for everything. We only had about 4, 5, 7 at the most flakes across that entire 1,000 runs across all browsers. So really, this test doesn't have any more flakiness on any one browser than the other. If we look at a different test, this one is logging in as a guest user. This one is really interesting because on IE10, we have a large amount of flake. It's kind of hard to see on the graph here, but we can see all these red bars here are representing retries that have happened, and we actually count the number of retries. We had over 2,000 of them. So this gives developers on our dev team a place to look. They can look and see, okay, why is this one particular test flaking out so much more on IE10 than everything else? And if we go back to our friend amend, order, cancel, we can see that we've got a massive amount of flake that's behaving in a really interesting way. It's kind of flaky everywhere on IE11, Chrome, and Firefox, but on Edge and IE10, it's really, really flaky, like disproportionately flaky. So there's some interesting mysteries here about why is this happening? So what have we learned with all this data? So when trends really appear chaotic, just find another dimension. Keep slicing until you can separate out a test that's behaving one way on one browser, or excuse me, behaving one way on one browser and another way in another browser. And just keep slicing until you can find a difference, and use those differences to narrow down the root causes. Because when we're looking for flake, instead of trying to pretend like it doesn't exist, it can be exciting when we find it, and even more exciting when we can narrow it down. We're still pretty early in the process of taking this data and actually figuring out what these root causes are, but some of the ones that we've identified already are long-running tests, as I mentioned, tests that are bumping up against that maximum 8-minute individual test time. Of course, we could increase that maximum to something else, but we'd rather not do that because that's going to jeopardize the health of our whole system. Live network calls are another one. We try to rely on our tests being completely mocked so that we can keep better control of them. And non-deterministic application bugs, real actual bugs in the app. So where do we go from here? Our roadmap for BLOOP is to open source it really soon, get more stats integrated into it, and something that we want to do in the next year is to actually take that data that we have in BLOOP and use that as an input into Magellan, into our test runner. Remember that orchestrator? So that we can actually determine the optimal order that we should run our tests based on their history of flake and timing. Because if you imagine this, like your tests are a rock, and longer running tests or flakier tests are bigger rocks, and shorter tests are kind of like smaller rocks or even little bits of sand. Anybody ever done this exercise where you try to put sand and rocks into a jar, and if you just put all the sand in first and then the rocks, it doesn't fit? But if you put the bigger rocks in first and then you pour the sand in, everything fits. So if we're trying to get to the point of a really friendly developer pull requests verification process and fitting this massive amount of testing into 5 minutes, then it actually could matter a lot the order that we run our tests. And if we're intelligent about ordering these based on the history that we've observed, then we can get to a happy developer who's spending less time waiting. So I encourage everybody to join the community. Check us out at Test Armada on GitHub. Follow us on Twitter if you want to stay up to date about BLOOP. Follow me. And one more time, say it with me. 1, 2, 3. Hooray for Flake! Come get stickers. Thanks, everybody.